In this lesson, we're going to look at curves in space. So let's start by drawing our x-axis in space and then our y-axis. So here's our y-axis, and this is in three-dimensional space. And then we have our z-axis. And imagine that we have a bug, and it's flying around in three-dimensional space. It does a little loop here, and off it goes. And it's moving with respect to t, and in this particular case, t means time. So what we can do is we can look at it at any point. Say our starting point is here. We have some radius from the origin to the position of our bug. Let's say that this is P represents our position, any point in space at a given time. So for each time we have a radius, which is a vector from the origin to the point where the bug resides. And in this particular case, our r is r at time 0. This is the starting point. Now after a second, the bug could be at this location. So what I'm going to do is let's move this up so we have a little more room here. So we have a new r, and that's r at time 1. And then maybe at time is 2 seconds, our bug is here. So this becomes our r vector at time 2. And then at 3 seconds, we have an r vector at time 3, and so forth. So we could say, well, here we are with an r vector, r, at time t sub I, some specific time. So r, our vector r, is equal to some function f of t in the I direction plus another function g of t in the j direction plus a third function h of t in the k direction. Now, the question is the path that the bug takes, which is defined by the r vector, which changes over time. Is this path continuous? Which means, is r of t continuous? Well, it is continuous if the limit for any value t sub naught. So it is continuous at t equals t sub naught if the limit as t approaches t sub naught for r of t is equal to another vector L of t. Now let's look at this from a different perspective. Another way of saying this is to say that the limit as t approaches some value t naught of the magnitude of the difference between r of t and L of t must equal 0. So this is an easier way to determine continuity, is when we're looking at the difference between these two vectors and the magnitude of the difference. And it should be 0 if the limit as t goes to t naught for r of t is equal to L of t. So let's start with our R vector, which is a function of time, and it has components in the I, j, and k direction, where our first is some function of time, and that's in the I direction, another function of time in the j direction, and a third function of time in the k direction. That's our R vector. Then we have our L vector, which is not a function of time. It just exists. It's a vector. We're approaching this. This is what we approach as t approaches some value t naught. So we have it's equal to some real number in the times in the I direction, a, and then a real number b in the j direction, plus a real number c in the k direction. And remember, we're saying that the limit as time approaches some value t naught for r of t is this limit vector L. So let's move this up. And so this is the same as saying that the limit as t approaches t naught of the magnitude of r of t minus L is equal to 0. So to work this limit out, we would say, what is the limit as t approaches t naught of the square root of f of t minus a squared plus g of t minus b squared plus h of t minus c squared. And I'm hoping that you recognize this as the formula for magnitude. Now remember, we're checking for continuity, and we want to know, is r of t continuous as t approaches some value t naught? So we can break this down by looking at these individual components. And this limit exists if the limit as t approaches t naught of f of t is equal to a, and the limit as t approaches t naught for g of t equals b, and the limit as t approaches t naught for h of t equals c. And if these are all true, then r of t is continuous at t equal to the value t naught. And the limit as t approaches t naught for r of t is equal to L. Here we have a path that a particle follows, and at a specific time we have a vector r of t, and then at a time in the future we have r of t plus a delta t, where delta r, which is this, is equal to r of t plus delta t minus r of t. So the derivative r prime of t is equal to the limit as t, in this case t is time, approaches 0, of delta r over delta t. And this gives us the instantaneous rate of change, or velocity, because we have direction and magnitude. And this instantaneous velocity is tangential to the curve of motion. So if we have a vector function r of t as follows, and we want to find r prime of t, then what we're going to do is take the derivative of each component. So it's equal to the derivative of f of t with respect to time in the I direction plus the derivative of g with respect to time in the j direction plus the derivative of h with respect to time in the k direction. Now this gives us the velocity, and we could take the magnitude to get the speed. So this is our velocity vector. If we want the speed, we'll take the magnitude of this. And if we want the acceleration, we're going to take the second derivative with respect to time. So this is our velocity vector. And the second one is our acceleration vector. And that's going to be the second derivative for the acceleration vector. It's the second derivative of f of t with respect to time in the I direction plus the second derivative of g of t with respect to time in the j direction plus the second derivative of h of t with respect to time in the k direction. And this gives us our acceleration. So if you have a vector r and a vector s, and you take their sum, and you want to find the derivative of their sum, then that's going to be, you're going to take the derivative of r plus the derivative of s. And that could also be true for the difference. So if you took the difference of r and s and took that derivative, it's the same as taking the difference of their individual derivatives. So now let's look at products. If we have r and we take the product, the dot product of r and s, and we want to take the derivative of that, that's going to be the derivative of r times s, vector s, plus the derivative of vector s times vector r. Now, if we want to take the cross product of r and s, and we want to find that derivative, this is going to give us r prime cross with s plus r cross with s prime. And then if we have some function f times our vector r, and we want to find that derivative. That's going to be f prime times r plus f times vector r prime. Okay, so let's start with the vector function r of t and say that it's equal to t plus 3 in the I direction plus t squared minus 4 in the j direction. So if we want to find r prime of t, or the derivative of r with respect to time, put this an arrow over that. So we want to find the derivative of r with respect to time, then we're going to find r of t prime, and it's going to be the derivative of t plus 3 with respect to time, and the derivative of t, of course, is 1. So that's just going to be 1i, or just I, plus, now we have to take the derivative of t squared minus 4 with respect to time, and that's 2t, and that's in the j direction. Now if we want to find, so that's velocity. That's our velocity vector. So our velocity vector is I plus 2tj. Now if we want to find the second derivative of r with respect to time, well, the derivative of 1i is just 0, and then the derivative of 2tj is 2 in the j direction. So the second derivative has one component, 2j, and that's our acceleration vector. So we're accelerating 2 units in the j direction. And if we want to determine the velocity and acceleration at t is equal to, say, 2 seconds, then we know that the velocity vector at 2 seconds, the velocity, is going to equal to, and we're going to go up here, and of course the velocity is I plus 2tj, so it's going to be 1 in the I direction, plus 2 times 2, which is 4, in the j direction. That's our velocity. And our acceleration vector at time equals 2 is going to be 2 in the j direction. And if we want to find an equation in the xy plane for this vector, well, our x component is t plus 3, and our y component is t squared plus 4. So let's write that down. So we would say that x is equal to t plus 3, and y is equal to t squared minus 4. And if we look at the equation above and we solve for t, we get t is equal to x minus 3. And if we take our x minus 3, which is our value for t, and we substitute it into our y equation for t, we're going to get y is equal to x minus 3 squared minus 4, which is y is equal to x squared minus 6x plus 9 minus 4, and let's combine our last two terms and we get y is equal to x squared minus 6x plus 5. So here what we have is our equation of y in terms of x, and we have our acceleration and velocity at time t is equal to 2.